Machine level programming, systems architecture, and then what is assembly and object code. So here we're going to look at what is C code, how is it translated to assembly, and then how is that translated to machine code. So an architecture is an instruction set architecture is usually what it's called. It's the part of the processor design that you need to understand when you write assembly code or when an instruction is being executed. So you can think of the architecture as being a contract between the programmer and the machine to behave in a certain way. So the machine will have a set of specific specifications for what the instructions do. It might have a common set of memory, registers, for example, that are then common across all implementations of that architecture. Then the microarchitecture is an implementation of a given architecture. And the microarchitecture might change not just by cache sizes and core frequency, but how something is actually implemented. So maybe how addition operations are performed, or how many instructions can execute at the same time within the processor. There are two code forms that we're going to be looking at, one of which is machine code. So that's the byte level programs that a processor actually executes. So machine code represents instructions as series of binary, bytes, where the bits mean certain kinds of instructions. So just as we saw that bits can mean, a certain pattern of bits can mean the number 42 or the letter X or a floating point number 7.5, here they will also be able to represent specific instructions like move this from here to there, or add these two numbers, these two locations together. Machine code is in these numbers. It's not really in numbers. It's what we see as numbers. But that's what we sort of conceptualize the machine using. But then for humans, there is an assembly code. That is a more written version of those instructions. So an assembly code might actually say add as opposed to the specific encoded bit pattern that means add. So examples of this, example instruction set architectures, x86, IA32, Itanium, x86, 64, those are all Intel instruction architectures. ARM is another instruction set architecture. There are multiple variants of it, just like there are for the x86 or for the Intel architectures. And there are many different, although ARM is a single specification for an architecture, there are many different chips that implement that same instruction set architecture. And they're made by different companies. So like by Samsung, by ARM, some by Intel, some by various Chinese companies. So at the assembly or machine code level, this is about the simplest diagram that we can have to explain what goes on in the processor. So the first thing we have is a memory over here. And the memory is just that byte addressable array abstraction that we had. And memory is where all the code and user data is stored. And we also will then see that we're going to have an abstraction of a stack, kind of like the stack you have or we'll learn about in data structures. And that's to support procedure calls. The memory has a simple interface to the actual processor itself. The processor will send an address, or in other words, the name or address of a memory location, and then the processor or the memory will send back data. Or the processor might send an address and send data to write data into the memory. The other thing that happens is the processor needs to have instructions to know what to be able to execute. And so, again, a similar kind of case will be in addition to data, the CPU might send an address and then get instructions back from memory. The processor itself is shown over here in the salmon blob over here. So one of the abstractions in a processor, and I'm using the word abstractions because these things, these are the way that you should think of the machine implementing it, but it's usually implemented in a slightly different model or a slightly different way. So PC, or the program counter, this is always the address of the next instruction. And in the x86 machine, or the 64-bit machine, it's called the RIP. So it's the register instruction pointer. It used to be called the instruction pointer in the IE32 computers. Then there's a series of registers. Registers are basically where frequently used values can be stored and then operated on. So the processor cannot directly operate on anything in memory. To be able to add two numbers together if they're in the memory, both of the values will need to be brought over, put into a register, so one value and then the other, and then you will operate on the registers themselves. So that's where you can actually say, now add these two registers together, and then you would need to store the data back into the memory. So the registers are a small amount of memory that you can explicitly name into which to store items in memory and to operate on them. Condition codes are related to the outcomes of operations. So we store status information about the most recent arithmetic operation or logical operation. So things that are stored in the condition codes are going to be things like, when I added the last two numbers together, were they even, or were they zero, or was there a carry out when I added that? And those are used for conditional operations like conditional branches and if then else statements. When we take a typical C program, so if we have a program like P1 and P2, we need to turn it into an executable program at the end of the day. That's the thing that's actually going to be given to the CPU to execute. So our C program, the first thing we do is we're going to compile that C program. So this is an example of a command line. Here we're using the GNU C compiler, GCC. And this is an option to GCC saying, I want you to optimize the program, mean make it more efficient, perhaps. And then I want you to take both P1.C and P2.C and turn them into an executable that is called P. So that -O here means output. The resulting binary will be in this file P, but the steps that happen are we compile the programs, and so here you might get errors and other things along these lines. And when that program is compiled, it will then produce an assembly program that is a text file that is then assembled by either GCC or an assembler AS. So in other words, we can actually get the assembly code corresponding to our C code dumped out so that we could look at it if we wanted to. Then the assembly code, which is again still human readable at this point, is now turned into a binary format called an object file. So this would be P1.0 and P2.0. So an object program, the assembly operations have been translated into their corresponding machine representations. So in other words, just the numbers. Then there's usually a phase called linking that occurs. And in the linking phase, you'll take libraries. So for example, your program might use a routine like printf or malloc or the sign routine or something like that. It's going to pull that in from some libraries and then combine that with your program to produce an executable program. There's a later phase called loading, which is once you actually have your executable program, you have to give it to the operating system to be able to execute. So when we turn C code into assembly code, that process, we can just do this here, and we'll do this in our labs. You'll take a look at being able to do this for a specific sample program. But here we have a C program. We have a plus routine that looks like it just adds two numbers together. Here we have a sum store routine. This is not great code, but the idea is that we want to have small routines that we can examine and take a look at. This code, if it's compiled, would look something like this over here. So I actually did recently compile this program today on one of my Linux computers, and I got more or less exactly the same sequence of operations here. You might get slightly different operations on different machines because the process of translating from C to assembly, that's the compiler's role, and it may find that certain sequences of instructions are more efficient than others, or better to be able to execute, or maybe the compiler has been improved so that it can do something a lot more efficiently than it used to be able to do. This code is so simple that it's going to look pretty much exactly the same when you try and compile it today. If you were to compile this on a Macintosh, Mac OS system, you would see the same instructions here, probably. And if you did it on a Windows computer, you would also see probably the same instructions. There might again be some slight differences in the way that that code gets rendered. But both Mac and Windows use x86 CPUs, as do Linux, and all of them would produce assembly code somewhat similar to this. Because the assembly code is related to the underlying machine, and then what's called the ABI, the application binary interface, that the operating system uses. And for this example, they'd be all close enough. So there's two kinds of x86 assembly code. And if you're the Intel or Microsoft world, so MASM stands for Microsoft Assembly, you'll see a different syntax. We use what's called the AT&T and then GAS, which is the GNU assembler syntax. In the GNU assembler syntax, we have a mnemonic, meaning an instruction like add, and then there's a source and destination. So the operations go from left to right. So we might see, for example, add something to something left to right. In the Intel instruction set, you might see, for example, an instruction add, and then this is the destination, this is the source. So things go from they go from left to right up here, right to left down here. And up here, we'll see that the addressing and a few other things are slightly different in this, the AT&T and the GAS syntax. We're going to be using this syntax because we're making the assumption that you're going to be using a Linux computer, which is either what our online system is or the virtual machine that you're going to be using. But you will come across this other assembly format as well. So just to be clear, in this course, we're going to see the GAS or AT&T syntax, where it's a mnemonic and instruction and then a source and destination. So for example, here there's an instruction add, and then these are the names of two registers. And what this corresponds to is the register RBX, so this is a left to right. RBX is assigned RBX plus RAX. So this basically means add this to that. Add RAX to RBX and leave it in RBX. Assembly language has doesn't really have any data types. The only kind of data types that it has are integer-sized data, so data of size 1, 2, 4, or 8 bytes, and then these are data values. When data is put into registers, we don't really know what kind of data it is. In other words, when we load data from memory, we don't know whether it's a signed integer or an unsigned integer. There's nothing in the data that tells us that. We don't know whether it's really a data value or whether it's addresses or whether it might even be floating point data. We have to remember what we want the data to believe, and that's the compiler's job. Floating point data is usually typically 4 or 8 bytes on the x86, and sometimes there's something a 10 byte floating point value, but you probably won't see that. Code winds up being byte sequences encoding different series of instructions. So code will be decoded automatically by the processor. The only thing that we do with decoding code is calling or routines or jumping to someplace. There are no aggregate data types such as arrays or structures or classes or linked lists or none of that. All of memory is just contiguously allocated bytes of data. And so any of those structures would be a contiguous region in memory. So if I have an array, that'll be just a bunch of data in a portion of memory that I'm going to treat as an array. And likewise, if I have a C++ class or a C struct, That's just some data that happens to be near other data in memory in adjacent or contiguously allocated chunks. In assembly code, we perform very simple operations. So we perform arithmetic functions on registers or memory data. So much of our time is actually spent transferring data between memory and registers. So loading data from memories into registers and storing register data into memory. This constitutes typically 20% of the time of every process of a CPU. 20% of the time is just moving data back and forth. And then there's control transfers. So this is how we sequence in what we're actually executing. So we'll see that we have what are called unconditional jumps and procedure calls, and this is all implemented in hardware. And then what are called conditional branches, that's used to implement an if then else. Object code looks like, so if, again, we can't look into memory, so all we can do is we can look into memory and say, oh, I'm going to treat this as unsigned hexadecimal values and print it out. That's what we did here. These values that are being shown here are actually the encoded values of the instructions for the sum store function that we had before. Now, how do I know that these are instructions instead of integer numbers? Well, in this case, it's because my title tells me so. If you were just to encounter this in memory, you would not necessarily know, like if it was some part of memory, you would not know that these are necessarily instructions. They could be data as far as you're concerned. And it's really important to get this insight that one of the magical features about the way that stored program computers were designed is that one program's code might be another program's data. So for example, the compiler is producing data, object files, that is another program, right? Because programs can manipulate programs. That's the really powerful insight that made computers be really powerful. That was sort of Turing's insight into computers. So this code has a total of 14 bytes. In this code, each instruction is 1, 3, or 5 bytes. And this is the starting address up here where that code starts. So this is a hexadecimal address. It's down low in memory, closer to 0 than up high. The assembler has translated the .s file, the assembly code, into binary files. And then when it all gets linked and merged between different, with all the different library routines and so forth, all of that code would be merged into your binary. Most computers now use what's called dynamic linking. Instead of taking the printf code and sticking it into your library or into your program directly, we have a mechanism by which you can call a common shared version of printf. That helps reduce the amount of memory that's devoted to library routines like that. But more importantly, if we update the one shared copy of printf, if there's a security problem or something like that, then all programs that use it will also be updated. The linking phase occurs for dynamically linked programs when the program starts execution, not when it's being compiled. For statically linked programs, the linking process is when the program is being built or compiled. So here's an example of a machine instruction. So this is a pointer over here. So dest is an address of some place in memory. And what we're saying here is store the value t into the memory location designated by dest. So star dest or splat dest, that means dereference the value that dest is pointing to and stick t into it. That winds up being this single instruction here. So this is moving an 8-byte value, and I'm going to know it's 8-byte because it's doing a quad word here. So it's going to move a quad word from this register, the RAX register, into the memory location pointed to by the RBX register. So the value t in our program is being represented by the RAX register, and the value dest is being represented by RBX. And then the star dest is being, in other words, the take dest as an address and use that to go to memory, that's being represented by the parentheses that are around it. If we look at that as object code, it would look like this here. So this is the instruction that actually encodes this move quad operation. So again, all this is doing is the same C code up here. So these are three different representations of the same concept, the same statement that's being done. We can disassemble object code. There's a program called objdump that you'll use for some assignments later on. And so if you have a .o file or an executable file, you can say, I want to give a disassembly of that, and it will then show you all of the instructions in each subroutine in the program. So these would have been all of the instructions in the sum store routine. Here's our encoded in our machine code version, and then here's our assembly code version. This over here is the address that this particular instruction is at. So you'll see that some instructions, so for example, the push, it takes only a single byte. The pop is a single byte, so on. Here the call instruction has multiple bytes associated with it. The move and these two move instructions also have multiple bytes associated with them. You can see here that this move instruction and this one here and this one here are clearly similar to one another, right? So they both start off 488903. This one has a D3 up here, and this has an O3 here. And we'll see that that's basically the difference between whether I'm encoding this or encoding that in the instruction. So in later assignments, you're going to wind up taking a binary program for which you do not have the source code, and you are going to disassemble that program and figure out how it functions and what it's doing internally. So one really useful tool for this is objdump. There's another very useful tool, and this is an online system called onlinedisassembler.com. And in onlinedisassembler.com, you can upload a binary file, and it will then chunk it up, and it can give you a diagram like this. So this is some code where there's something happening at the beginning of a function here, and then this is a loop as denoted by the green arrow here that's looping here, and then this is some exiting code after the loop is done and when we're done with our function. If you use objdump, you'll have to locate the looping code and the if-then-elses and make your own diagrams like this. It's much easier to use the online disassembler to be able to do that. This is a free system. You can sign up for an account to do something, but as far as I know, you don't need to sign up, and it doesn't ask you for money. There are other ways to disassemble code. So we're going to be going through tutorials about how to use the GNU debugger to do that. So you can start up the GNU debugger as a, let's say, running the sum program, and then you can say disassemble the sum store function, and this is what it will give you here. It'll disassemble the code at a particular point. You can also examine the 14 bytes in hexadecimal at wherever sum store is stored, and that would give you this here. So here this is showing you the 14 bytes that is at that representation. Again, this could be data. It could be, when we say examine memory and show it to me as bytes, we can examine any part of memory and it will display it to us in bytes. It's not going to know whether it's floating point data, instructions, whether it's strings, whether it's your fancy image for your game. It's just bytes. Data is always just bytes inside the machine, and what we make of it is how we decide to perceive it, whether we look at it as instructions or as integer data or floating point data. So what can be disassembled? Well, we could disassemble the Word program for Windows, but reverse engineering programs are forbidden by the Microsoft end user license agreement. But that doesn't mean that people don't do that. So security compromises are often found by taking an executable file, disassembling it, and then trying to look for certain classes of exploits. We'll be looking at some of those later on in the class, the kinds of exploits that you might find and be able to compromise a machine on. People do the same things with operating systems. So if you've ever heard of jailbreaking an iPhone, what that is that somebody has sucked out the operating system out of the iPhone and then gone through and disassembled it and reverse engineered it to try and, again, find security exploits or problems that can be exploited in the operating system for that. But pretty much anything that can be interpreted as executable code can be disassembled. The disassembler just examines bytes and it reconstructs assembly source. There are actually some programs that are used in the security community. IDA is an example of this, that also will try to translate code into the C programming language, but it's a pretty coarse approximation of what was originally written.